Have you ever stopped to truly consider what's happening when something burns? I mean, really think about it.
Yeah, like the glow from a candle, maybe?
Exactly that comforting glow. Or, the sheer power you hear in a bus engine starting up.
Hmm.
It's more than just flickers and warmth, isn't it?
It absolutely is. It's this fundamental process, a kind of microscopic dance, really.
A dance that powers our whole world. Sometimes for good, sometimes, no, not so good.
Totally. From the little flame on your gas stove making dinner
Useful.
to the giant engines pushing planes across the sky, fires just everywhere. But what is it? Like fundamentally, what's happening chemically?
And how does burning actually work? What secrets does it hold about, I don't know, energy and change?
Well, if you're curious about that, you are definitely in the right place today.
Yes. Welcome, everyone, to the Deep Dive. I'm Adam.
And I'm Grace.
And we're grade 8 science teachers here at School on X.
And today, our mission, should you choose to accept it,
Haha.
always, is to take a really, really detailed look at combustion and flame. That's Chapter 4 in your grade 8 science curriculum.
Yeah, we're not just scratching the surface here. We want to peel back all the layers on this. It's pretty fascinating stuff when you get into it.
Our goal today is to break down, well, everything. What fire is, chemically speaking, what it absolutely needs to even exist.
Right, these essential ingredients.
And then how we can control it, because obviously that's important.
Very important.
Plus, the different ways things can burn, it's not all the same. And even, the bigger picture, its impact on our planet.
We really want to turn that curiosity you might have just from seeing fire into like a deep understanding. We're aiming for those aha moments.
Those moments that make science genuinely exciting, maybe even a bit awe-inspiring.
Okay, let's dive in then, starting right at the beginning. What exactly is combustion? At that chemical level, what is actually burning?
Okay, so at its absolute core, combustion is a chemical process, and it's a rapid one.
Rapid
Think of it like a substance reacting like really energetically with oxygen.
oxygen from the air.
Usually, yes, from the air around us. And when this intense reaction happens, it releases energy, mostly as heat.
Which is why fire feels hot. Makes sense.
Exactly, sometimes searingly hot. And often it gives off light, too. That could be the flame you see dancing around, or sometimes just a steady glow. It's basically stored energy being let out.
So if something can do this energetic dance with oxygen and release heat, we call it combustible. Is that the term?
That's the one. A combustible substance. It's the fuel, essentially.
Right.
The material that's ready and willing to react with oxygen.
Okay, so wood, paper, those are combustible.
Perfect examples. Wood, paper, kerosene oil, like you might use in a lamp, the LPG gas in a cooking cylinder. They'll all readily catch fire and keep burning. They're packed with potential fuel.
But then there are things that just won't burn. The opposite. What's the term for those?
We call those non-combustible. Simple as that. Substances that just don't undergo combustion no matter how much heat you reasonably apply.
Like the iron nails in my toolbox.
Or a piece of stone.
Exactly. Iron nails, stone pieces, glass, they just won't ignite. They might get really, really hot if you put them in a fire, maybe even glow red hot.
Right.
But they won't burn. They won't sustain that chemical reaction. That's the key difference. Can you think of other examples around you, maybe at school or home?
Okay. Like maybe a ceramic plate versus a paper napkin. The napkin burns easily, the plate definitely doesn't.
Perfect distinction. What can burn versus what can't. It seems obvious, but it's fundamental to understanding fire.
Now, you mentioned something really interesting before, connecting this to our own bodies. How does that work? I think we touched on this in class 7, maybe.
We did. It's a fascinating connection. Think about food. We always call food the fuel for our bodies.
Yeah, like petrol for a car.
Yeah.
Food powers us, keeps us going.
Exactly. And in a really amazing way, what happens inside our bodies is a form of controlled combustion. It's much slower, much more complex, obviously.
How so? Well, the food we eat, the carbohydrates, fats, proteins, it gets broken down, and through a series of very complicated chemical reactions, it reacts with the oxygen we breathe in.
Ah, the oxygen connection again.
Always the oxygen. And this slow, steady process releases energy. It produces the heat that keeps our body temperature stable, the energy that lets our muscles move, our brains think. Everything.
So it's like a really, really slow, gentle fire inside us.
That's a great way to think about it. A highly controlled, super efficient burn. The underlying principle combining fuel with oxygen to release energy is exactly the same as a bonfire, just much more sophisticated. It's biological engineering at its finest.
Wow. Okay, that makes lunch seem Way more scientific. So if food is our fuel and oxygen is key, what about fire in the outside world? What are the absolute must-haves, the conditions needed for that chemical dance of combustion to actually start and keep going?
Right, there are three absolute essentials. You can think of it like a triangle, the fire triangle. You need all three sides for it to stand. Take away even one side.
And the whole thing collapses, the fire goes out.
Precisely. The fire either won't start or it will stop pretty quickly. It's a delicate balance.
Okay, let's break down this triangle.
Yes.
What's the first side? The first essential ingredient?
The first one is air, or more specifically, the oxygen in the air. Oxygen makes up about, 21% of the air we breathe?
Right around that.
And its role is absolutely vital. We can actually see this really clearly with a simple experiment, activity 4.2 in the textbook, the candle experiment.
Ah, yes, the candle under the chimney. I remember this one. Walk us through it.
Okay, imagine you've got a candle lit, burning nicely on a table. First step. You take a glass chimney, like an open glass tube, and place it over the candle. But you prop it up a little bit, maybe on a couple of small wooden blocks.
So air can get in underneath.
Exactly. Air flows in freely from the bottom. What happens to the candle flame?
It just keeps burning normally, right?
Mm.
Steady flame, nice and bright, plenty of air.
Correct. Plenty of oxygen supply. Okay, scenario 2. You remove those wooden blocks. Now the chimney rests directly on the table. Air can still get in a bit, maybe, but it's much more restricted.
Okay. What happens then? Does it change?
It does. The flame usually starts to flicker a bit. It might even produce some smoke. You can see it's kind of struggling.
Like it's gasping for air.
That's a great analogy. The oxygen supply is limited, so the combustion isn't as complete or steady. It's fighting.
Okay, and the final step. Cut off the air completely.
Final step. Take a flat glass plate or something similar and cover the top of the chimney. Now, no fresh air can get in from the top or the bottom easily. What's the immediate result?
Like goes out, right? Poof.
Instantly, it extinguishes, sometimes with a final little puff of smoke. This whole sequence just proves it so clearly.
Yeah.
Air, specifically the oxygen in the air, is absolutely necessary for combustion. Cut off the oxygen.
And you kill the fire. That's why smothering works, like with a fire blanket.
Exactly. You're removing one side of that essential fire triangle, the air supply. Same principle.
Makes total sense. Okay, so oxygen is side one. What's the second essential ingredient? You mentioned heat before.
Yes. The second crucial piece is heat, but not just any heat. It's about reaching a specific point called the ignition temperature.
Ignition temperature. Okay, what does that mean exactly?
It's a threshold. It's the absolute lowest temperature that a particular substance needs to reach before it will actually catch fire and continue to burn on its own. It has to get hot enough for the combustion reaction to become self-sustaining.
So it's not enough for something just to get warm. It has to hit that specific trigger point.
Precisely. Think about a matchstick just sitting there on the table.
Right. It's made of wood, paper, chemicals, definitely combustible. There's oxygen all around it. Why doesn't it just burst into flames?
Good question. Because it hasn't reached its ignition temperature? Room temperature isn't hot enough. It needs that little extra oomph, that spark of heat.
The friction when you strike it.
Exactly. And the story of the matchstick itself is pretty cool, actually. A great example of applied science solving a real problem. People used to start fires with much harder methods for ages, right? Flint and steel, reaping sticks.
Yeah, must have taken ages sometime.
Oh, definitely. Even the early matches they had in places like ancient Egypt were just bits of pine wood dipped in sulfur needed an existing flame to light. But the modern safety match, that's only about 200 years old. And the first versions, well, they weren't so safe.
What was wrong with them?
They often used white phosphorus on the match head. White phosphorus has a very low ignition temperature. It could literally ignite just from the friction of being rubbed against almost any rough surface.
Whoa, that sounds dangerous. Like accidentally setting your pocket on fire?
Absolutely possible. And worse, white phosphorus is highly poisonous. It caused terrible health problems for the factory workers making the matches, a horrible disease called phossy jaw. It was a real issue.
Yikes. So how do they make them safer, the ones we use today?
Science figured out a clever workaround. Today's safety match head contains different chemicals, mostly antimony trisulfide and potassium chlorate. The real trick is the striking surface on the side of the box.
The rough bit. What's on there?
That has powdered glass to create friction and a tiny amount of red phosphorus. Red phosphorus is much more stable, much less reactive than white phosphorus.
Okay, so what happens when you strike the match?
The friction generates just enough heat right at that point of contact to convert a microscopic amount of the stable red phosphorus on the box into the highly reactive white phosphorus.
Ah, so it creates the dangerous stuff just for a split second.
Exactly. And that newly formed white phosphorus immediately reacts with the potassium chlorate in the match head. That reaction produces a quick burst of intense heat.
And that heat is enough.
That heat is enough to raise the antimony trisulfide in the match head to its ignition temperature. And then, boom, you get a controlled flame. It's really quite an ingenious chemical sequence.
That is genuinely clever, turning something dangerous into something safe and useful through chemistry.
And this whole idea of ignition temperature explains why some fuels are so much easier to light than others. Think about kerosene oil versus a big log of wood.
Kerosene seems way more flammable.
It is. It has a much lower ignition temperature than wood. A small spark near kerosene can easily set it alight. Wood needs a lot more heat for a longer time to get it to its ignition point.
That's why you need kindling, right? Like small twigs or paper to start a campfire.
Precisely. The kindling has a lower ignition temperature. It catches fire easily from a match. Then, the heat from the burning kindling is enough to raise the temperature of the bigger logs until they reach their ignition temperature and start burning. It's a chain reaction, all governed by these temperature thresholds.
It also explains why you have to be so careful storing things like kerosene or petrol.
Absolutely. Their low ignition temperature makes them a fire hazard if not handled properly. Special storage, keeping them away from heat sources. It's all about preventing them from reaching that critical point.
Now, speaking of ignition temperature and seemingly impossible things, there's that amazing paper cup experiment, Activity 4.4. It still blows my mind a bit.
Haha, yeah, it's a classic. It seems like it shouldn't work at all. You take 2 paper cups.
Just normal, flimsy paper cups.
Yep. One you leave empty. The other you fill with some water, maybe about 50 milliliters. Then you hold both of them, one after the other, over a candle flame.
The empty one obviously catches fire pretty much instantly. Paper burns.
Of course. But what happens to the paper cup with the water inside when you hold it over the flame?
It doesn't burn. The paper stays intact, even though the flame is catching it. And the water inside actually gets hot. You can even boil water this way, right?
You absolutely can boil water in a paper cup over a candle. It seems like magic, but it's pure science.
So how does it work? Why doesn't the paper burn?
It's all about heat transfer. The heat from the candle flame gets transferred to the paper cup, but then the paper immediately transfers that heat to the water inside through conduction.
Ah, the water acts like a heat sink.
Exactly. Water is fantastic at absorbing heat without its own temperature shooting up too quickly. It has a high specific heat capacity. As long as there's water in that cup, it keeps pulling the heat away from the paper.
So the paper itself never actually reaches its ignition temperature.
That's the key. The heat gets whisked away into the water fast enough to keep the paper below the point where it would ignite. It's a brilliant demonstration of how managing heat can prevent combustion, even with flammable materials.
That really is cool. Okay, so this leads to another important term, especially for safety signs we see everywhere. Inflammable substances.
Yeah.
What makes something inflammable?
Right, inflammable, which confusingly means the same as flammable, refers to substances that have very low ignition temperatures.
So they catch fire really, really easily.
Extremely easily. Often just a small spark or tiny flame is enough. Think petrol, alcohol, LPG gas, even some spray aerosols. They tend to vaporize easily too, creating flammable fumes.
And that's why they need such careful handling and storage. All those warning labels.
Precisely. Because they ignite so readily and can burn very rapidly, sometimes explosively, the precautions are absolutely necessary. Those no smoking signs at petrol stations aren't just suggestions.
Definitely not. Okay, so we know what combustion is. We know it needs fuel, oxygen, and enough heat to reach ignition temperature. Now, what about when we want the fire to stop? How do we control flames? How do we put fires out?
Well, it all comes back to that fire triangle we talked about: fuel, air, oxygen, and heat.
The 3 essential sides.
To extinguish a fire, the basic strategy is always the same. You need to remove at least one of those 3 essential requirements. Break the triangle.
So take away the fuel or cut off the air or cool it down below the ignition temperature.
Exactly. That's what all firefighting methods aim to do, whether it's a simple bucket of water or a sophisticated chemical extinguisher. Remove one or more sides of the triangle.
Okay, let's talk about the most common one first. Water. When is water a good firefighter?
Water is fantastic, the go-to extinguisher for what are called Class A fires. These involve ordinary combustible materials, things like wood, paper, cloth, trash.
The kind of fire you might see in a burning building or a bonfire getting out of control.
Exactly. You see fire brigades using hoses to drench these fires. And water works in two really effective ways simultaneously.
Two ways. What are they?
First, the most obvious one, cooling. Water absorbs a huge amount of heat. When you spray water on burning material, it rapidly cools it down, bringing its temperature below its ignition point.
So it stops the fuel from being hot enough to burn, removes the heat side of the triangle.
Correct. But there's a second effect, too. When that water hits the hot fire, it turns into steam very quickly.
Right, you see massive clouds of steam sometimes.
And steam takes up way more volume than liquid water. This expanding steam cloud pushes away or displaces the surrounding air, effectively cutting off the oxygen supply to the fire.
Ah, so it attacks the air side of the triangle too, cooling and smothering. That's clever.
It's a very effective 1-2 punch for those Class A fires. But, and this is a huge, but water has some really critical limitations. It can be dangerous in certain situations.
Okay, this sounds like really important safety information, especially for you grade 8 learners listening. When should you absolutely not use water on a fire?
Number one, absolutely crucial. Never use water on electrical fires. Fires involving live electrical equipment, appliances, wiring, anything plugged in or connected to the power grid.
Why is that so dangerous?
Because water, especially tap water with impurities, conducts electricity really well. If you spray water on live electrical gear that's on fire, the electricity can travel right through the stream of water.
Straight to the person holding the hose or bucket.
Exactly, leading to severe electric shock or even electrocution. It's incredibly hazardous. Plus, it can damage the equipment even further. So for electrical fires, water is a definite no-go.
Okay, rule 1. No water on electrical fires. What else?
Rule 2. Water is also useless, and actually dangerous, for fires involving flammable liquids like oil or petrol. Think of a pan of cooking oil catching fire on the stove, or a petrol spill igniting.
Why doesn't water work there? It seems like it should cool it down.
The problem is density. Water is heavier than oil and petrol. So if you pour water onto burning oil,
It just sinks underneath.
it sinks right underneath, leaving the lighter oil or petrol floating on top, still burning. Even worse, the force of the water can splash the burning liquid, spreading the fire rapidly. It makes the situation much, much worse.
Wow, okay, so no water on electrical fires and no water on oil or petrol fires. That's vital to remember. So if water's out for those, what do we use? Who's the hero extinguisher then?
For those tricky Class B flammable liquids and Class C electrical fires, the modern hero is often carbon dioxide.
CO2, like the gas we breathe out. How does that put out fires?
It's actually brilliant for these situations. It works through a different dual mechanism than water, and it avoids the dangers of conductivity and spreading liquids.
Okay, tell me more. How does CO2 fight fire?
Firstly, CO2 gas is significantly heavier or denser than oxygen. So when you release CO2 from an extinguisher, it rapidly expands and forms a heavy blanket over the fire.
It sinks down and covers the flames.
Exactly. It pushes the lighter oxygen away, effectively cutting off the air supply. It smothers the fire, takes away the air side of the triangle.
Like an invisible heavy blanket.
Perfect analogy, but there's more. CO2 has a second trick. It's stored in those extinguisher cylinders under very high pressure, usually as a liquid.
Right, I've seen those red cylinders.
When you release it, that liquid CO2 rapidly expands into a gas, and this rapid expansion process makes it incredibly cold, like super cold. It can reach temperatures around minus 78 degrees Celsius.
Oh, that's freezing.
It is. And this intense cold rapidly cools down the burning fuel, helping to bring it below its ignition temperature, so it attacks the heat side of the triangle too.
So CO2 smothers and cools, just like water, but safe for electrical and oil fires.
Precisely. It smothers by displacing oxygen, and it cools significantly upon expansion. Plus, it doesn't conduct electricity, it doesn't spread liquid fuels, and it leaves no messy residue behind, which is another bonus, especially for sensitive electrical equipment.
That makes it a really versatile extinguisher for those specific hazards.
Yeah.
How is it usually deployed? Just from those cylinders?
Mostly, yes. Stored as a liquid under pressure in those red cylinders, which you often see mounted on walls in workplaces or labs. You open the valve and out comes the cold CO2 gas. There are also some fire extinguishers that use dry chemical powders like sodium bicarbonate, basically baking soda or potassium bicarbonate.
Baking soda puts out fires.
It can. When these powders hit the heat of a fire, they decompose and release a large amount of CO2 gas right at the source, which then smothers the flame. So it's another way to deliver CO2 to the fire front.
Fascinating how much science goes into just putting out fire safely and effectively. Okay, let's shift focus slightly. We've talked about what fire needs and how to stop it. But fire itself isn't always the same, is it? Sometimes it's slow, sometimes fast, sometimes explosive.
Absolutely. The way combustion happens can vary dramatically. We can generally classify it into a few main types based on how fast and violently it occurs.
Okay, what's the first type? The most common one, maybe?
Let's start with rapid combustion. This is what we usually think of as typical burning.
Like lighting the gas stove.
Perfect example. You turn on the gas, introduce a flame, and whoosh, it burns quickly, steadily, producing heat and light almost instantly. Burning paper is another example of rapid combustion. It's fast, noticeable, and often controlled.
Okay, rapid combustion. Then there's the really dramatic one, spontaneous combustion. Sounds like something from a sci-fi movie.
It does sound dramatic, and it can be. Spontaneous combustion is when something bursts into flames seemingly all by itself, without any obvious external spark or flame being applied.
How on earth does that happen? Magic.
Haha, not magic, just chemistry. It happens when a substance slowly reacts with oxygen at room temperature, a very slow oxidation. This slow reaction generates a tiny bit of heat. If this heat can't escape easily, like if the material is piled up or insulated,
The temperature slowly builds up.
exactly, it builds and builds bit by bit until the material reaches its own ignition temperature. Then suddenly, it ignites. We mentioned white phosphorus doing this earlier.
Right, just catching fire in air.
But it's not just weird chemicals. It can happen with everyday materials under the right or maybe wrong conditions. Coal dust is a classic, tragic example.
In coal mines.
Yes. Fine coal dust can slowly oxidize. If it accumulates in poorly ventilated areas, the heat builds up, and it can lead to devastating fires or explosions underground. It's been the cause of many mining disasters.
That's terrifying. What about forest fires? Can they start spontaneously?
Some can, yes. Sometimes intense heat from the sun can trigger it in very dry vegetation. Lightning strikes are another natural cause. But sadly, a huge number of forest fires that seem spontaneous are actually caused by human carelessness.
Ah, like leaving a campfire still smoldering.
Precisely. Or discarding a cigarette butt improperly, or even piles of oily rags left in a corner of a workshop. The oil can slowly oxidize, generate heat, and ignite the rags. It highlights how careful we need to be. A seemingly dead campfire can reignite hours later if not properly extinguished with water and stirring.
That's a really important point about responsibility. Okay, so we have rapid and spontaneous. What's the third type?
The third type is an explosion. Think fireworks or crackers during a festival.
Bang. Lots of light and sound. Very fast.
Extremely fast. An explosion is a combustion reaction that happens incredibly rapidly, almost instantaneously. It releases a large amount of heat, light, and sound, and crucially, produces a huge volume of gas very quickly.
It's the rapid gas expansion that causes the bang.
Largely, yes. The sudden creation and expansion of gases exert enormous pressure outwards. Sometimes explosions can also happen just from pressure building up rapidly inside a container, even without a direct flame, like if an aerosol can gets too hot. It's combustion happening with extreme speed and force.
So many different faces of fire. Now, what about the flame itself? You see different colors sometimes, like the blue flame on a gas stove versus the yellow flame of a candle. Does the flame tell us something?
It tells us a lot, actually.
Yep.
The appearance of a flame, its color and structure, gives us clues about what is burning and how efficiently it's burning. And a key factor here is vaporization.
Vaporization, like turning into a gas.
Exactly. Only substances that vaporize turn into a gas when they are heated will actually produce a visible flame when they burn.
Okay, so like kerosene, it gets hot, turns into a vapor, and the vapor burns with a flame.
Yes. Or the wax in a candle. It melts, gets drawn up the wick, gets hot enough to vaporize, and it's those wax vapors that are actually burning and creating the flame you see.
So what about something that doesn't vaporize easily, like charcoal?
Good example. Charcoal doesn't really vaporize when heated. It just gets incredibly hot and reacts with oxygen directly on its surface. So it glows intensely red, gives off a lot of heat, but you don't see a distinct flickering flame like you do with a candle. No vaporization, no flame.
That's a neat distinction. Can we actually prove that it's the vapors burning in a candle?
We can. There's another simple experiment, activity 4.5 again. If you take a lit candle that's not flickering too much and carefully hold a thin, clean glass tube with tongs,
Okay.
and introduce one end of the tube into the dark zone of the flame right near the wick where the unburnt vapors are.
The coolest part we talked about earlier.
Right. And then quickly bring a lighted matchstick near the other end of the glass tube. What do you see?
Does a flame appear at the other end of the tube, away from the candle?
It does. A small flame will ignite at the open end of the tube. This shows that the wax vapors from the candle's dark zone traveled through the tube and are now burning when they meet the match flame. It's proof that the invisible vapor is the fuel for the flame.
That's very cool. Visual proof. Now, you mentioned zones in the flame. A candle flame isn't just one uniform thing, is it? It has structure.
It has a surprisingly complex structure, like a tiny chemical factory with different areas doing different things. We can even find evidence of what's happening in these zones. For example, remember the unburnt carbon particles?
Yeah, soot, basically.
If you hold a clean glass slide or plate with tongs and introduce it into the luminous part of the flame, the bright yellow bit, for just about 10 seconds,
What happens to the glass?
you'll see a blackish circular ring deposited on the glass that soot those unburnt carbon particles. It tells us that combustion in that bright yellow zone isn't complete. It's making leftovers, if you like.
So the yellow part isn't the most efficient part, even though it's the brightest.
Correct. It's bright because of those glowing hot carbon particles, but their presence means the fuel isn't burning fully. Now, what about finding the hottest part?
How do we do that?
You can take a thin copper wire. Copper's good because it shows heat well. Hold the wire with tongs just inside the outermost edge of the flame, the part that's almost invisible, maybe slightly blue. Hold it there for maybe 30 seconds.
Oh, I see.
You'll notice the part of the copper wire in that outermost zone starts to glow red hot very quickly. Much hotter and faster than if you put it into the yellow part.
Ah, so that faint outer edge is actually the hottest place in the flame.
It is indeed. That tells us combustion is most complete and therefore hottest, right at the edge where the fuel vapors meet plenty of fresh oxygen from the air.
So based on all this, we can really break down a candle flame into distinct zones.
Absolutely. There are 3 main zones we typically identify, starting right at the center, near the wick, the innermost zone. It's dark.
Why dark?
Because it's full of unburnt wax vapors that have just come off the wick. There's very little oxygen here, so no real combustion is happening. It's actually the least hot part of the flame.
Okay, innermost, dark, least hot, full of vapor. What's next?
Moving outwards, you get the middle zone. This is the bright yellow luminous part that we usually think of as the flame.
The part that makes the soot.
Exactly. This is where partial combustion happens. There's some oxygen, but not enough to burn the wax vapors completely. So it produces those tiny carbon particles. They get heated until they glow yellow. That's incandescence. And that's what gives the candle most of its light. It's luminous, but not the hottest and a bit inefficient.
And the last zone, the one that made the copper wire glow.
That's the outermost zone. It's often very faint, almost invisible, sometimes with a slight blue tinge. This is where complete combustion occurs.
Why complete?
Because this outer layer has the best access to fresh oxygen from the surrounding air. The fuel vapors here can react fully. And because the combustion is complete, it releases the maximum amount of energy, making this the hottest part of the flame. Not very bright, but very hot.
Wow. Innermost, dark, cool, unburnt. Middle, yellow, bright, partial burn, soot. Outermost, faint blue, complete burn, hottest. That's quite detailed for a simple flame.
Isn't it? And this knowledge isn't just academic. It has practical uses. Think about goldsmiths.
People who work with gold and silver, melting and shaping them.
Exactly. They need very high temperatures to melt those metals. Do you know how they achieve that with just a simple flame?
Do they use the flame differently?
They do. They use a thin metal blowpipe. They blow air through it, directing the flame. But critically, they direct the outermost non-luminous part of the flame onto the metal.
They specifically target the hottest zone.
Precisely. By using the blowpipe to focus that zone of complete combustion, they get the maximum heat right where they need it to melt the gold or silver efficiently. It's a centuries-old craft based on understanding the physics of a flame. Real applied science.
That is a fantastic example. Okay, so we've dissected fire and flames. Let's zoom out again and talk about the stuff we burn on purpose. Fuels. What makes a fuel?
Well, a good fuel. Is there such a thing as a perfect one?
That's a great question. In an ideal world, the perfect fuel would have a whole checklist of desirable qualities.
Okay, like what? What's
Yeah.
on the wish list?
Well, ideally, it should be easy to get hold of, readily available. And cheap wouldn't hurt either.
Availability and cost, got it.
It should burn easily in air, but not too easily or uncontrollably. You want a moderate, steady rate of burning.
Makes sense. Not an explosion unless you want one.
Right. And crucially, it needs to produce a large amount of heat for the amount of fuel you use. We call this having a high calorific value, lots of energy packed in.
High energy output. Okay. Anything else? And finally, the dream fuel wouldn't leave behind any nasty stuff after burning no unwanted residues like ash or soot, and definitely no harmful polluting gases. Clean burning.
Readily available, cheap, burns easily but moderately, high energy output, and clean. That sounds too good to be true. Does any fuel actually meet all those criteria?
Honestly, not really. There's no single fuel that perfectly ticks every single one of those boxes for every situation. It's always a trade-off.
So it's about finding the best fit for a particular job.
Exactly. Think about wood. In many parts of the world, it's very available, relatively cheap. Good points. But it produces a lot of smoke and ash when it burns, which isn't great for health or cleanliness. And if you cut down too much wood, that causes deforestation. So trade-offs.
Okay, what about something like LPG, the gas many people use for cooking?
LPG burns much more cleanly than wood, produces a lot of heat efficiently, big pluses, but you need special pressurized cylinders to store and transport it. It costs more than wood in many places, and it's derived from fossil fuels. Again, trade-offs. Every fuel has its pros and cons depending on the context.
That's why we use so many different kinds, I guess. We usually group them by state, right? So solid, liquid, gas.
We do. Solid fuels include things like wood, coal, charcoal, even dried cow dung in some places. Liquid fuels are your kerosene, petrol, gasoline, diesel, and gaseous fuels include LPG, CNG, compressed natural gas, biogas, hydrogen. Each type has different properties, storage needs, and applications.
Now, you mentioned calorific value, getting a lot of heat out.
Yeah.
How do we actually measure that? How do we compare how much energy different fuels give us?
That's where the scientific term calorific value comes in. It's the standard way to measure fuel efficiency in terms of heat output.
Okay, what's the precise definition?
The calorific value of a fuel is defined as the amount of heat energy produced when 1 kilogram of that fuel is completely burned, complete combustion.
So how much heat energy you get from burning exactly 1 kilogram?
Exactly. And we measure this heat energy in units called kilojoules. So the unit for calorific value is kilojoules per kilogram, written as kJ/kg.
Kilojoules per kilogram. Okay. Does this value differ a lot between fuels?
Hugely. And looking at the numbers really makes it clear why we choose certain fuels for certain jobs. Let's take some examples from the textbook tables. Cow dung cakes.
Still used a lot for cooking fuel in rural areas of many countries.
Right. Their calorific value is relatively low, around 6,000 to 8,000 kilograms. Wood is better, maybe 17,000 to 22,000 kilograms.
Okay, a definite improvement.
What about coal? Coal is higher again, maybe 25,000 to 33,000 kilograms, depending on the type. Now compare that to LPG.
The cooking gas, what's its value?
LPG is way up there at around 55,000 kilograms.
Wow, that's more than double coal and way more than wood or dung.
Exactly. And then you have something like hydrogen gas, which people talk about as a future fuel. Its calorific value is enormous, around 150,000 kilograms.
Incredible. So you need much less LPG or hydrogen by weight to get the same amount of heat as you would from wood or coal.
Precisely. This huge difference in calorific value explains why LPG is so much more efficient for cooking than wood, even if wood is cheaper. You get far more heat energy from each kilogram of LPG burned. Higher calorific value means more energy bang for your buck.
That makes sense.
Yeah.
So fuels give us all this wonderful energy. But there's a flip side, isn't there? A dark side to all this burning.
Unfortunately, yes. A very significant dark side. The widespread burning of fuels, especially fossil fuels, has some serious harmful consequences for our health and the environment. This is something really critical for you grade 8 students to understand as it affects your future directly.
Okay, let's break down these harmful effects. What's the first major problem?
One big issue comes from incomplete combustion, especially of carbon-based fuels like wood, coal, and petroleum products. When they don't burn fully, they release tiny, tiny particles of unburnt carbon, essentially soot, into the air.
We saw that with the candle flame depositing soot on the glass. Are these particles dangerous?
Yes, very. Because they're so fine, they're easily inhaled deep into our lungs. They are major air pollutants and can cause or worsen respiratory problems like asthma, bronchitis, and other lung diseases. That hazy smog you see over cities often contains a lot of these fine particles.
Okay, unburnt carbon particles are bad for breathing. What else?
Another product of incomplete combustion is a gas called carbon monoxide,
Okay.
AO.
I've heard this one is really dangerous. The silent killer.
That's the one. It's extremely poisonous. The danger is that it binds to the hemoglobin in your red blood cells much more effectively than oxygen does.
So it stops your blood from carrying oxygen.
Exactly. It essentially suffocates you from the inside by preventing oxygen from getting to your body's tissues and organs. And the truly terrifying thing is, carbon monoxide is colorless, odorless, and tasteless. You can't detect it with your senses.
So you wouldn't even know you're breathing it in?
Not until it's potentially too late. This is why it's critically important, and this is a major safety warning. Never ever burn coal, charcoal, or even use portable gas heaters in a poorly ventilated or closed room, especially overnight. The CO can build up silently and kill people sleeping there. It's a tragic but preventable consequence.
Wow, okay, that's a very serious warning.
Mm-hmm.
What about carbon dioxide, CO2? We breathe it out, plants use it, but burning fuels produces loads of it too, right? Is that a problem?
It has become a major global problem, yes.
Yeah.
While CO2 is a natural part of the atmosphere, the massive amounts released from burning fossil fuels, coal, oil, natural gas, since the Industrial Revolution have significantly increased its concentration in the atmosphere.
And why is more CO2 a problem?
Because CO2 is a greenhouse gas. It traps heat in the Earth's atmosphere. More CO2 means more trapped heat, leading to a gradual increase in the planet's average temperature. This is what we call global warming.
And global warming has consequences, doesn't it? It's not just about slightly warmer weather.
No, the consequences are far-reaching and serious. Rising global temperatures cause polar ice caps and glaciers to melt faster, which leads to rising sea levels.
Which threatens coastal areas.
Yes, potentially causing flooding, displacing millions of people, and even submerging low-lying islands and coastal regions entirely. It also disrupts weather patterns, leading to more extreme events like heat waves, droughts, heavy rainfall, and more intense storms. It's a huge challenge for the entire planet linked directly to our fuel consumption.
Okay, so unburned carbon, carbon monoxide, carbon dioxide.
Yeah.
Are there other harmful pollutants from burning fuels?
Yes, unfortunately. Burning coal and diesel in particular releases significant amounts of sulfur dioxide, SO2, and burning petrol, gasoline, in engines releases oxides of nitrogen.
Sulfur dioxide and nitrogen oxides, what do?
They are both pretty nasty gases on their own, suffocating, corrosive, bad for respiratory health, contributing to smog. But a major environmental impact happens when they get released into the atmosphere. They react with water vapor and oxygen up there.
And they form acids.
Exactly. They dissolve in rainwater to form sulfuric acid and nitric acid. This makes the rain acidic, what we call acid rain.
Acid rain sounds bad. What kind of damage does it cause?
It's very damaging. It harms forests by damaging leaves and making the soil acidic, which harms trees. It acidifies lakes and rivers, killing fish and other aquatic life. And it corrodes buildings, statues, and historical monuments, especially those made of limestone or marble. It literally eats away at the stone over time. It's a widespread problem affecting ecosystems and our cultural heritage.
Goodness. Unburnt carbon, CO, CO2, acid rain.
Yeah.
It's quite a list of problems caused by burning fuels. Is there any good news? Are we finding cleaner ways?
Yes, absolutely. There is hope, and a lot of effort is going into finding and using cleaner fuels and developing more efficient combustion technologies. One good example that's already widely used is compressed natural gas, or CNG.
CNG. I've seen buses and cars that run on that. How is it cleaner?
CNG burns much more cleanly than petrol or diesel. It produces significantly fewer harmful pollutants, much less unburnt carbon particles, very little carbon monoxide, and negligible sulfur oxides. While it still produces CO2 when burned, contributing to global warming, its overall pollution footprint is much smaller, making it a cleaner fuel choice, especially for vehicles and cities.
So it's a step in the right direction.
It is. And beyond CNG, there's ongoing research and development into fuels like hydrogen, which we mentioned has a very high calorific value. When hydrogen burns, the main product is just water vapor, H2O.
Wow, just water. That sounds incredibly clean.
It does, although producing, storing, and distributing hydrogen safely and efficiently still presents challenges. But it shows the direction things are moving towards reducing the harmful byproducts of combustion. Science and innovation are key to finding sustainable energy solutions.
That's a hopeful note to end on. We have covered an incredible amount today. From the tiny chemical reaction in a flame.
All the way to the huge global impacts of burning fuel, it really has been a deep dive into combustion and flame, Chapter 4.
We defined what combustion actually is, that rapid reaction with oxygen.
We explored the fire triangle, the absolute essentials, fuel, air, and ignition temperature.
We looked at how to put fires out by removing one of those essentials and why water isn't always the answer, leading us to CO2.
We classified the different types: rapid, spontaneous, explosive, and even peed inside a candle flame to see its hidden zones.
And finally, we talked about fuels themselves, what makes a good one, how we measure their energy with calorific value.
And faced the serious environmental consequences: pollution, global warming, acid rain, but also look towards cleaner alternatives like CNG. It all connects.
And for all you grade 8 students listening from School on X, understanding this chapter isn't just about science class.
Not at all. It's about being an informed citizen. The choices we make about energy, how we heat our homes, how we travel, the policies we support, they all relate back to the principles of combustion. Knowing how fire works, both its benefits and its dangers, really does shape our future.
So as you go about your day now, maybe when you see a candle burning, or notice the exhaust from a bus, or even light the stove, perhaps you'll see it with new eyes, thinking about those reactions and impacts.
We've taken something common like fire and broken it down today, but think about this. What other everyday things, if you really did a deep dive into them, might reveal surprising connections to big scientific ideas or global challenges? What's the next mystery hiding in plain sight that you want to unravel?
Keep that curiosity burning.